And this was the point in my project where everything stopped. This is my poor asteroid.
The asteroid too.
Everything. This poor guy. So I'm taking images. This one. And then so then this blob appears, and I'm really curious about it, so I take more pictures. And it gets darker. And it eventually swallows my asteroid. And so I talked to Dr. Bill, and we decided that we would send the CCD back to the manufacturer to see what's wrong. One thought was maybe that moisture had gotten in on the CCD, and so when you cool it to -30, it's going to freeze and block photons. But we never did figure out, because, yeah. So this is where I started my second project. I got some images from Dr. Bill of Trojan asteroids from Kitt Peak. And I started to measure them. So when you're measuring an object, you only want the counts from the source. You don't want the counts from the sky. There is a signal from the sky because the sky scatters light, like moonlight and city light. So you want to get that out of your measurement. So this is how we do that. So first you measure all of the counts within a given aperture around your object. And the counts in here are from the background, scattered light, and also from your source. Next you measure the background in this annulus. That's the gray stuff. And then you scale this so that you can get background signal per pixel, and you scale it to the area of the aperture and subtract. So then you're just left with the source. All right, so we have counts of electrons, and we want to be able to compare these results to other people's results. So we want to calibrate them to physical magnitudes. So what you do is when you observe your object, you also observe something called a flux standard star, which is just a star with a well agreed upon magnitude. And you measure the electron counts for these stars, and you can get a correlation between electron count and magnitude. And use that correlation to calibrate your electron count from your source to a magnitude for your source. Also, we're taking advantage of the linearity of the CCD. So if you double the amount of electrons, you get double the amount of flux from the star or the asteroid. So here is the first light curve I made, and this is one of the asteroids that they observed at Kitt Peak. They observed it for 3 nights in a row, and this is varying brightness as a function of hours from the first exposure they took. But this isn't too useful in regards to knowing about the rotation of the asteroid, so we want to convert the x-axis to be in terms of the phase of the rotation for the asteroid. So what we do is we use previously published rotation periods for these asteroids and divide the exposure times by that, and we get a plot like this, this is one full rotation. And you can see that this was probably a bigger surface area illuminated to us, and that's probably a smaller one. And so here are the 4 that I made. And these 2 look pretty typical. There's some scatter here. But this one is pretty flat. So I would say maybe we're looking down the axis of rotation, or the shape is not very elongated. And this one looks really funky, and that's because, or at least we think that the published period was incorrect. So we're still trying to figure out what the period of this is. And that's it. Does anyone have any questions?
Thanks.
Yeah.
What about the way the last data looks makes you think that I mean, obviously it looks weird, but what about the weirdness makes you think the published period is wrong?
Well, we have 3 minima here. You should have 2 minima in one phase, in one rotation. And so 2 of these should line up. Yes?
Did you take some sort of time-variable curve to it and try to
there is a program called PDM that we're working with now, and you can input all of these data points, and it gives you a graph of possible periods, and you just check all of those. And so we're working on that.
More questions?
What are they possibly composed of?
We're not sure. They could be like the main belt asteroids, which is mostly rock, or they could be more like comets, where they would have some ice in it. But that's something of interest, is to compare the two and maybe see if they came from different places.
So what's the, I'm sure people have ideas. Are there?
I don't know. Maybe they're thinking that that Jupiter captured these stray Kuiper Belt objects or something from the Oort cloud. I'm not sure. I haven't really read up on what all the theories are. But
Is this some of the first data then? What's going on now? Is that, or how mature is the field?
I don't have a feeling for how mature it is.
How long? I think you could review instead of.
People have light curves in these things that are not very nice. They're fainter than the main belt asteroids are a lot brighter, and there's a lot of light curves beyond the feed. There are very few, and there are very few. There's only a few where they've looked at different years. You have to do that because the rotational, the orbital period is like 12 years. So you have to look at least 3 or 4 years to see at different angles. People only have. I've only done that for 1 or 2.
Oh, it's pretty. Okay.
Yes.
The scatter there, is that your error, or is that?
I'm not sure. I didn't go too much into error analysis of the data, so I'm not sure.
Okay. Thanks, speaker. Once again.